This lesson is part of a larger unit on thermochemistry. Specifically, this is going to cover heating and cooling curves, heat of fusion, and heat of vaporization. If you do not have these materials, please pause the video and get these materials right now. You're going to need a pencil, paper, some reference table or other reference that gives specific heats, heat of fusions, and heat of vaporizations. And you'll also need a scientific calculator. So a quick review. Temperature is a measure of the average kinetic energy of particles in a substance. Kinetic energy is energy due to motion. So the faster particles are moving, the higher temperature they have. Now, keep in mind, since temperature is a measure of the average kinetic energy, that doesn't mean that all the particles have the same kinetic energy. It just means that, on average, particles are moving faster. Potential energy is energy due to position. For example, if I have a book on top of a desk, that book has more potential energy than a book on the floor. Now in chemistry, we'll talk about particles and their relative distance from each other as increasing or decreasing potential energy. Also remember that heat and temperature are related through the equation Q equals mc sub P delta T. New definitions that you'll need to know. Heating and cooling curve. It's a plot of temperature versus heat for a particular substance. It'll show you temperatures at which this substance is a solid, liquid, or gas, and it'll also show you the temperatures at which a substance will undergo a phase change. In other words, when a substance will be at its melting point or its boiling point. Heat of fusion is the energy needed to melt 1 gram of a substance. Keep in mind, this word fusion is used elsewhere in chemistry, but here it means melting. When a substance goes from a solid to a liquid, another term that can be used is fusion. It's not often used, but here is another example of where you see this word fusion. For water, this value is 334 joules per gram. Now, the heat of vaporization is the energy needed to vaporize or turn from liquid to a gas, 1 gram of a substance. For water, this value is 2,260 joules per gram, a much larger value than the heat of fusion, which makes sense because if you're looking at the potential energy of particles in the liquid phase going from the gas phase, that's a much larger change than going from the solid phase to the liquid phase. So let's look at an actual heating and cooling curve. This would be considered a heating curve. A cooling curve would just have a negative slope. You see here I have temperature on the y-axis and heat energy on the x-axis. And so as we add heat energy, we see that at times the temperature changes. Now, sometimes the temperature doesn't change. Why? We'll get to that in a little bit. So let's talk about the different phases. So where would the solid phase go? Where would the liquid phase go? Where would the gas phase go? The solid phase is going to be of lowest energy. That's going to be on the line AB. Liquid on line CD, medium energy, and the gas phase is going to be on line EF. Now, where does melting occur when the substance goes from solid to a liquid? Obviously, hopefully you can see that this is on line BC. On line BC, you're going to have both phases present, solid and liquid. On point B, you'll only have the solid phase, and on point C, you'll only have the liquid phase. Likewise on line DE, you're going to have the liquid gas phase, both existing on that line. And yes, point D just liquid, point E just gas. Now, let's come back to that question. Why isn't the temperature changing during a phase change? We're adding heat. Heat is increasing. Why isn't the temperature changing? Well, if you guess because of the type of energy that is changing, you're correct. When something isn't in a phase change and is just in one phase, then the temperature increases. Like we talked about before, since temperature is a measure of the average kinetic energy of particles in a substance, then when a substance is in only one phase, an increase in temperature means that the kinetic energy is increasing. So what kind of energy is changing when a substance goes through a phase change? Now, I've already alluded to it before, previous in this video. It is potential energy. Potential energy is going to change. Those particles are going from the solid to the liquid phase. They're going from a rigid structure to flowing past each other. Their potential energy, their position relative to each other, is increasing. Likewise, from going from a liquid to a gas, the potential energy is changing. You're going from a liquid that has the particles flowing next to each other but still relatively close to being very far apart from each other in the gas phase. That is a large difference in potential energy. How close those particles are to each other, or I should say, going from the liquid to the gas phase, how much further they're increasing from each other, increasing that potential energy. So it's important to note here that a substance is going to not increase in temperature during that phase change, but once all of it is converted to that one phase, then the temperature can begin to change. With a heating curve, it's going to start to go up. With a cooling curve, it would just start to go down. So a heating curve and a cooling curve can be very useful for us when we're looking at types of calculations that we could be doing. Before, we've already covered Q equals mc sub p delta T, as you see in green here, that you can use for a substance in the solid, liquid, or gas phase. But what if we're given a situation where a block of ice at, say, negative 12 degrees Celsius increases in temperature to liquid at 25 degrees Celsius? What energy change is associated? Sorry, what energy is associated with that change, and what kinds of changes is that substance going to undergo? So imagine this. Imagine, say, negative 12, right about there, 25 degrees Celsius, right about there. So you can calculate the energy needed go from negative 12 to 0 of solid, and of 0 of liquid to 25 degrees Celsius of liquid. But what energy is needed to actually melt that substance? Here's where our heat of fusion will come in. Q equals m h sub f. H sub f being the heat of fusion, m being the mass, and Q being energy in joules most of the time. So now, what about going from a liquid to a gas? That's going to be our heat of vaporization. Q equals m h sub v. So keep in mind here that these values are different. For a particular substance, they're different. Same thing for the specific heat. Depending on what phase it is in, that specific heat value is going to be different. So we could, if we knew the mass of water, in my previous example, calculate the energy associated with that. But I have some other problems that we're going to do first before we jump into a large calculation like that. But just for the sake of this, how many different steps would that be? It would be 3. You would calculate this energy, and this, and then you would add them all together. Add. So now I want to show you what some actual heating curves look like if you were to plot these in a lab. Perhaps we can find a good virtual lab that you can do where you can see this, but really doing one of these in the lab, you'll see this kind of data. It's not going to be that clean, those clean lines like we had before, but it's going to be more like a curve, like the actual name suggests. Okay, both of these are heating curves because you see the temperature increasing. So this one, you just have points, and you would just connect them with lines to get that curve. So let's do this first problem. How much energy is required to melt 15.0 grams of water? Well, Have we done a problem like this before? No, we haven't. So we're talking about melting, which means that we're going to have to use the heat of fusion of water. So Q equals M H sub F. The mass, 15 grams. The heat of fusion of water, if you remember, all the way back here, 334 joules. Let's go ahead and write this value down because we're going to need that one too. 2,260. Okay. 334 joules per gram. Grams cancel out. And I'm left with joules, which is good. Put this in our trusty, dusty, handy, dandy calculator. And we get 5,010. To the correct number of sig figs would be 5,010 joules. 3 sig figs. 3 sig figs. Just like specific heat should never limit how many sig figs you have, never let heat of fusions or heat of vaporizations limit how many sig figs you have. Okay, so we didn't need the 2,260 joules per gram heat of vaporization for water in that previous problem, but make sure you have it copied down because we'll need it in the next problem. Let's look at example problem number 2. And by next, I mean the one after this. So how much energy is required to turn 25.0 grams of ice at negative 5 degrees Celsius to liquid water? So in this particular problem, it's a little bit more difficult. We're right over here at negative 5 degrees Celsius, or sorry, yeah, it was negative 5 degrees Celsius. And we want to be right here at liquid water. It doesn't say that the temperature is anything higher than 0. It just says that it's going from negative 5 degrees Celsius of ice to liquid water. So that means we're going to have to do 2 calculations. We're going to have to do one with this one to see how much energy is needed to go from negative 5 to 0 of ice. And then we're going to need to calculate, using this equation right here, how much energy is needed to go from ice to liquid water. So that means that we're going to have to use Q equals MC sub P delta T, and Q equals MH sub F. So, the mass, 25 grams. The specific heat of ice, 2.11, and the change in temperature is going to be 5.00. Okay, now for the heat of fusion, we have 25.0 grams, and the heat of fusion, if you remember, is 334 joules per gram. And we'll need to plug each of these into our calculator and then add. The first one, I'm getting 264 because I need 3 sig figs, joules. And for the second one, I'm getting 8,350 joules. So the answer, how much energy? This is total energy. So we need to take 264, add it to 8,350. And I'm getting 8,610 to the correct number of sig figs. And that is our answer. Now, let's look at this problem. How much energy is required to turn 45.6 grams of ice at negative 13 degrees Celsius to steam at 103.00 degrees Celsius? How many steps is that going to be? Well, let's look back here. So we're at negative 13, and we're going all the way to 103. So negative 13, 103. So we need to go from here to here. That's 1. Here to here. That's 2. Here to here. That's 3. Here to here. 4. Here to here. 5. 5 steps. Then add them together. So I've already done this problem for you. So I just want to walk through each step because I feel like I made a video of me doing this, but I feel like I can walk you through each step and have a bit more conversation about it. So as we look at the heating curve, we talked about how we're going to have 5 different calculations. So we got 1, 2, 3, right there's 4, and then here we have our 5th one. Then we're going to have to take all of those energy values and add them up over here. That's by attempt at an arrow. So for ice, we were taking Q equals mc sub p delta T and finding the energy needed to turn that ice from negative 13 to 0 degrees Celsius. So if you see here, my value for the change in temperature is 13 because we're going from negative 13 degrees Celsius to 0 of ice. We use the specific heat of ice given from this table over here, or you can use the other reference table. And reference tables might not always agree with each other, but they're going to be close, so it's okay. And then we have the mass of the sample here, which, if you notice, isn't going to change throughout the entire problem. So we multiply all those together, and we get 1,250 recorded to the correct number of sig figs. I encourage you to please pause your computer through each step and just make sure you're getting that in your calculator as well. So the next step is the energy needed to melt this sample of ice. So again, the mass is the same, and the heat of fusion for water is 334, and so we're going to multiply those values into the correct number of sig figs. We get 15,200 joules. Then we're going from liquid water at 0 degrees Celsius to liquid water at 100 degrees Celsius. So that is a change in temperature of 100. Now, it is liquid water, so we have the specific heat of liquid water. Again, the mass stays the same. And if you find the product of that, rounded to the correct number of sig figs, which is 3. I was trying to keep it simple throughout this problem and always have 3 sig figs. It's going to get a little complicated when we get to the end and we have to add those values, but that's okay. I'll explain there. So then we need to find the energy needed to boil this sample of water. Again, the mass doesn't change. We're going to use the heat of vaporization for water, which is 2,260. And we have the product of that is going to be rounded to the correct number of sig figs, 103,000 joules. Then lastly, we're going to need to figure out how much energy is needed to go from 100 degrees Celsius of the steam to 103 degrees Celsius. So again, the mass doesn't change. We need the specific heat of water vapor, which is 2 from the table above. And the change in temperature, 100 to 103. Again, I'm using absolute values, 3 degrees Celsius. So the product of that is 274. So then if we take all 5 of those values and add them together, we're going to get in our calculator 138,824. I encourage you to pause your computer and make sure you're getting that. Okay, so this is where it gets a little interesting. We have to remember our sig figs for adding and subtracting, which is we record to whichever number has the least number of decimal places. Or in other words, whichever number has the last sig fig that is the largest place. Here, this is going to be 103,000, where the 3 is the thousands place, so we're going to have to round to the thousands place. So this 138,824 becomes 139,000 joules, or we could say that it's 139 kilojoules. Now, let's think for a second. Was energy leaving this system or going into the system? If you said going into the system, you are correct, which means that this value should be a positive value. And something that I missed in the previous problems, in problem number 2, it should also have been positive, as well as problem number 1. Now keep in mind, if it's a cooling curve, or if the substance is going from a liquid to a solid, or a gas to a liquid, or if it's freezing, or if it's condensing, then your value for the heat is going to be negative. So I hope that was useful. This does conclude this presentation. Please let your professor or teacher know if you have any questions.